of this unit, we're looking at a test. I'd hoped to do it late this week. I'm thinking it's probably going to end up being beginning of next week instead. I just don't feel like we're probably going to get through all this stuff this week. I want to give you a review assignment because I mean, we had that, winter break in the middle of this stuff. So you probably want to go back and maybe hit some of those earlier problems again, I'm guessing, before the test. So I'll give you a review assignment, put a practice test, and we'll go like beginning of next week. So click everything close. Let's get rid of earbuds, please. Thank you. And today we're looking at applications of linear systems. So these, now don't let this be one of those, oh man, moments when when you got to do word problems. Word problems are good. Like these word problems is bad. I mean, they have words in them, sure, but their application problems is really what they are. This is where you guys are more likely to use math in the future, is with some applications than pure math. Unless you're a math major, you would use this for some reason. You'd use math to solve some important problem. The problems we're doing today, these are problems that are going to look pretty familiar to you real soon. For example, in chemistry class. You guys in chemistry this year? Who's in chemistry this year? Okay. So you haven't seen this stuff yet, but you will. This will be, I think, second semester stuff where you'll do some problems like the ones we're going to look at today. So there will be, like, very, very soon, this will be something that's going to help you out, because a lot of times when people are doing chemistry, the problems that they have the most trouble with are the ones that involve lots of math. And so this will help you out a ton. This will really get you ready for those math-related problems. Like we're going to look at one today where you're mixing solutions. You want to get a certain concentration of acid. How would you create a certain concentration of hydrochloric acid, for example? We won't look at one like this in our examples, but the stuff we're doing will also help you when you use systems to balance equations second semester. You guys haven't done balancing equations yet, right? You're just starting that now. Oh, you did? Where you guys? Oh, you did. Did you use matrices for that? Okay. Okay. So we'll look at an example today that'll really help you with that stuff too. Okay. So I don't have a chem example, but the same ideas would apply. So applications of linear systems. The thing about applications, and we're getting to a point in your math careers where it's getting a little more interesting. That's the positive slant on it. Like you can't just go plug numbers into some formula and get an answer and call her good. I mean, everything's going to be a little bit different and unique when we look at applications problems. There is no one size fits all formula that's going to work. But there is a strategy. There's a general strategy that we can apply. Each step is going to look a little bit different for different problems, but the strategy is going to be the same. Essentially 3 steps involved in solving these kinds of applications applications of linear systems. So applied problems that are going to rely on linear systems to get a solution. First step when we're doing any kind of math application is always define your variables and write them down. Give your brain a break. Your brain is going to need to be focusing on step 2, setting up the equations. That's the part that's a little bit tricky and sometimes challenging. Step 1, defining the variables. Don't bog your brain down by asking it to memorize what the variables are too. Write that down so you can look at it when you need to jog your memory about what the variables represent. Okay, so write down what your variables are. Step 2, set up your equations. Now there's a really important concept here. If we end up having 2 variables, then we know, and this comes from what's called the first fundamental theorem of algebra, but we don't need to know that for now. We always know that the number of variables I have in my system determines the minimum number of equations I need to solve for those variables. So if I've got 2 variables, I have to have at least 2 equations. If I've got 5 variables, how many equations do I need? 5. I got to set up 5. That'd be a big system, right? And then step 3, I'm going to cut you some slack on this one, on the assignment and on this part of the test. Once you set up the system, you set up the equations in the system, you can use technology to solve the system. Okay, so the focus in this part is not really on the algebra, it's on the setting up the algebra. We'll let technology actually do the algebra for you though. So let's take an example. The sum of three numbers is 70. One number is 5 more than a second number. It is also twice the third. Find the numbers. So when you define your variables, you typically want to just go to the question. The question is going to ask about the things, the unknowns, and the unknowns are the variables, right? So what are the unknowns? What are the things we're trying to find here? The three numbers. Okay, so let's write these down then. What are we going to call x? I mean, what would you just think of a way to say that? What would x be then, maybe? Well, not 70. It's going to be one number. How about if we call it the first number? Okay, so x is the first of our three numbers. You guys know that means number, that symbol? Okay, what else does it mean? Okay, what else does it mean? Pound, yeah. Means all those things. There you go. Okay, so x is the first number. Y we could call the second number. And z be the third number. Okay, so how many equations do I need? Got to have three. Okay. So can anybody see a sentence there that's going to immediately give me an equation? Ah, there you go. Look at that. So the sum of the three numbers is 70. You always want to look for a total statement. If there's a total statement, that's always an easy equation because you're just adding up the unknowns to equal some total, right? So in this case, our first equation, I'll put a 1 there to remind us it's the first of three equations, is x plus y plus z equals 70. Okay? What about another sentence here? One number is 5 more than a second number. Translate that language into a math sentence, to an equation. What does is stand for? Equals. So one number, that must be our first number, right? So x equals 5 more than a second number. Yeah, what plus 5? Y plus 5. There you go. Second number plus 5. Okay. So there's our second equation. X equals y plus 5. And our third equation, it is also twice the third. Well, what's it refer to here? First number. There we go. So third equation, it x equals is twice the third number. How would I say that? 2z. Okay, we got them. Three equations. Three variables, three equations. There's our system. Good. Okay, now we do not want to rely on algebra to solve a 3x3 system. We didn't even do that, right? What did we do instead with a big system like that? How did we solve it? We used technology. Remember what we did? This was kind of right before break. That's it, right? We used matrices. We used the matrix calculator to solve a big system like this. Now you can solve any size system with a matrix. We could do a 2x2 system also, but we've got another trick for that that might even be simpler, okay? So we've got to write this as a matrix, but to write this as a matrix, the first thing we have to do is we have to put all the equations in what form? Standard form, right? They all have to line up. Everything has to line up vertically, doesn't it? Right? So we're going to put the variable terms on the left side and the constant on the right side. First one, do I have to do anything? It's already done, right? First one is good. X plus y plus z equals 70. Okay. Second one, though, I've got to do something. What do I need to do to the second equation? Yeah, I got to subtract the y over to the left side, don't I? And I want to line everything up vertically. So I've got x minus y equals, the equal signs need to line up, equals 5, right? Left with 5. How about the third equation? What do I have to do there? Yeah, I got to subtract the z term, the 2z, over to the left side because I need the z as a variable. It's got to be on the left side. So that's going to give me x, where am I going to put the minus 2z? Below the z. Minus 2z equals, well, what's left on that side if I subtract the 2z? 0. That's okay. 0 is a number, right? We just need a number on the right side. So there's my system. Now I've got to turn that into a matrix. Okay? We can do that. Okay, so what do I, help me out. What do I push here? New matrix. Got to push the new matrix button. Okay. Okay, how many rows do I need? 3, so I got to bump that up to 3 columns. 4, there we go. I need a column for each variable coefficient, and then another column for the other side of the equation, the numbers, the constants. So what goes in, let me make this bigger so everybody can see it. What goes in that first row? 1, 1. Good. Right, remember there's no variables in the matrix. We only put the coefficients in the matrix. Next row? 0, there we go, no z's. So we got 0, 5. Next one? Negative 2, 0. There it is. Okay. Perfect. Now what? Got to hit enter. Okay. How do I solve? RREF. What goes in there? A. I got to push the A buttons because I have to use matrix A. And there's my answer. How about that? Oops, that's too big. Well, that'll work. Okay. Yes. Anybody remember what RREF stands for? I would never expect anybody to remember this, but this is like reduced, reform, addition, reduced row echelon form. You were very close. Very close. Okay, yeah, so now let's make sense of all this. So our system, got to draw some arrows here. So our system, all this stuff corresponded to that matrix, didn't it? Right? We built the matrix, our original matrix, from our system, and then this gives us the solutions. What is this telling us? What's that first row telling me? Yeah, there it is. Look what this says. It says 1x plus 0y plus 0z. So that's just x, right? X equals 30. This row is telling me y equals 25. Okay, boom. How about that? All right. So when you guys do that chemistry stuff, did you use the reduced row echelon form, or did you guys have to do it differently? Okay. When you do those in college, you can just set up because you set up a matrix like this, didn't you? Right? You didn't? I thought you did. I think you did. When you balanced him, yeah. Didn't you guys set up? Okay, so you guys didn't use matrices for that? Oh, okay. 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 Okay, so when you do this in college, if you take a chem class in college, you'll be able to balance the equations by looking at the number of moles or molecules, whatever you're tracking, of each of the different elements. You can do it this way. So it's, and then the bar just goes in the middle. I want to say this, the equal sign could be, it could shift over to the left or the right a little bit. I don't want to get into too much, but this will be the technique you'll probably use in college to do this easily. Okay. Okay, how about this one? Who's in? Anybody in ag science? Nobody's in ag science here? Okay. Because you guys do stuff like this in ag science all the time, I know. Uh, did you? You did this? Okay. So did you guys, did you use like a, what do they call them, a Pearson square or something like that? Okay. So with the Pearson square, when you're mixing up percentages like this, you're making a, like some kind of a mix for an animal that, right? You you can only do two different ingredients in a Pearson square. The way we're going to look at this today, you could have as many as you want. You could have 5 different components of the mixture, because we're going to use a matrix method to solve this. It can be as big as you want, doesn't matter. How are we going to do this here? Let's read through it first of all. You got to really do that. When you're doing this on your own, read the question 2 or 3 times. It's going to take that long for your brain to kind of wrap itself around the question here. So soybean meal is 14% protein. So what's that mean, first of all? When you buy a sack of soybean meal, 14% protein, what's that telling us? Okay, 14% of the meal is pure protein, right? 86% is other stuff, non-protein, okay? Cornmeal is 7% protein. How many pounds of each should be mixed together in order to get 280 pounds of a mixture that is 13% protein? Because that's what we need for this animal. We need it to be exactly 13% for it to be optimum for, maybe these are, I don't know, horses or something. Who knows? Okay, cows, there you go. So step 1, what are the variables? What are the things I'm trying to find? And include the units. It really helps to include the units. What's, okay, well, X. What is X? Okay, but what about the soybeans? Is it the number of soybeans? The protein percentage. No, I'll read it again. Pounds, right? They want to know how many pounds of each are we going to include in our mix, okay? So X is pounds of soy meal. So what's Y then? There you go, pounds. Pounds of cornmeal. Okay, good. So there's my variables. How many variables? How many equations do we need? 2. Okay. So is there a total equation? Yes. 280. There it is. Good. Okay. 280 pounds. So equation 1, X plus Y, the number of pounds of soy meal plus the number of pounds of cornmeal, has to equal 280 total. There it is. Okay, now part 2. Part 2 has to do with the 13% stuff. Okay, we want to end up with 280 pounds of mix, but we want it to be 13% protein. So the other equation we need is to control the total amount of protein, right? So how much protein are we getting out of our mix total? How would I calculate it? But if we're making 280 pounds and we want our mixture to have 13% protein, how would I calculate the total pounds of pure protein? Okay, good, right? 1, 3. 1, 3 times 280, right? We're looking at the answer here. You're thinking about the other parts. I get what you're doing. That's good. Okay, yeah. Okay, what is that? Let's make a note of this. This is pounds, total pounds of pure protein. Okay, now we're getting somewhere. So whatever that number is, 0.13 times 280, that's just going to give us some number. That's going to tell us how many pounds of pure protein are included in our 280-pound mixture, right? Okay. Well, what's the other part of this now? We want to create that mixture. We're creating it from soy meal that has 14% protein. So what's going to be the total pounds of soy protein? Not soy meal. The soy meal is only 14% protein. I want just the protein. Times what? No. Hang on. What you guys already told me. What represents the total weight of the soy meal? X. There you go. Okay. So isn't that part right there, 0.14x, isn't that the total, that's the pure protein from the soy meal? Everybody agree? Okay. Pure protein from soy, right? I have to add that to the pure protein from the cornmeal to get the total amount of pure protein that we want. Okay. Whoops. 7% is 0.07. Why? There it is, right? Okay, so let's just kind of, what's that again? So that thing right here. Come on, there we go. Pure protein from cornmeal. Yeah, so the pounds of pure protein from soy plus the pounds of pure protein from corn equals the total pounds of pure protein that we want, which is 0.13 times 280, right? Make sense? Okay, there's our system. Look at that. That's easy. So we could use a matrix to do this. It's no problem. We could easily throw that in a matrix. I would just have the first row would be 1, 1, 280, right? What would the next row be? 0.14, 0.1, 0.07. Well, or I could just, I could, or I could just leave it like that if I want to. Desmos is smart. It knows to multiply that. 0.13 times 280, and it'll just make a number out of that. I could do that. What's plan B? What's the other technology avenue that I could take to get this answer without a matrix? Keeping in mind there's only two variables here, X and Y. Graphing, sure, right? If I have a system with only two variables, I could choose to just graph those as lines and look for the solution. You guys will tell me where to find the solution, but look at the graph to find the solution. Let's do this one that way. Okay, so where is this? Okay, first equation, x plus y equals 280. Okay, next equation, 0.14x plus 0.07y equals 0.13 times 280. Okay, all right. Where is it? Oh, yeah, I got to zoom out. There you go. Okay. There it is. That's helpful. Okay, so now where's the solution going to be then? The intersection, right there. Okay, so you guys help me interpret this then. What is that ordered pair telling me? What's the 240? What's the x coordinate telling me? Of soy meal, right? Because remember what the variables are. X is pounds of soy meal, and X is 240, right? So 240 pounds of soy. 40 means 40 pounds of corn. Okay? Give me thumbs. Does that make sense? Okay. Good, good. All right. Now you guys, let's take a look at this one. There's a chem question. You'll be doing stuff like this if you haven't already. So look, what are we doing here? How many liters of a solution of 6% hydrochloric acid and of 2% hydrochloric acid should be mixed to yield 80 liters of a 5% hydrochloric acid solution? Okay. Now let's think what that means. Like in chemistry, if you're talking about a 6% hydrochloric acid solution, how much pure acid is in that? 6%. What's the other part? What's the other stuff probably? Water. Yeah. Right. You're just mixing it in water. Okay. Pure HCl would be, you guys would never use that. That's way, it's just like you can't even breathe it. If you'd have to wear a respirator because just the fumes would burn your lungs. You can't do that. But if you have a real weak solution like this, it's okay. So you'd always be dealing with weaker solutions of acids, but you want to very carefully control the concentration of acid for safety reasons, but also because you want to get just enough acid to do the job. Like if you're trying to eat through some metal or something, well, there'll be a table that'll tell you to eat through steel, I need the concentration to be this. And so you want to build a solution that's just that, but no more, right? So this is kind of an important thing to be able to do. Okay, so uh, we're trying to figure out what are the variables here? What are the unknowns? What's being asked for? What are they asking for? Because those are the unknowns. Okay, liters of each of the two solutions. Okay, good. So then X equals liters of 6% hydrochloric acid, right? Y equals liters of 2% hydrochloric acid, okay? Two unknowns, how many equations? Two. Is there a total equation? What's the total? 80, yeah, right? We want 80 liters total, so that means X liters of the first type plus Y liters of the second type has to add up to 80 total liters. So there's one equation. X plus Y equals 80, okay? You guys do the rest. Go. Hop to the boards and try that out. Yeah, you bet. Hey, how's everything coming? Did you get some stuff done over break? Perfect. Good. All right. Yeah, you bet. Go ahead. There's our two equations. If we graph these guys, here's what you're going to get. You're going to get something like that, right? There's the intersection. And so what's that telling us? Well, that's telling us 60 liters of 6%, 20 liters of 2%. How about that? Good? Amazing. Okay. So, yeah, we are. How many we got left here? I think I have two left to do with you guys. Yeah, we'll just do those tomorrow. How about? Okay. Two more tomorrow, and then you'll be able to work the rest of the period. And I'll put a review assignment up. and we'll do probably an in-class review on Friday. Sound good? I'll kind of go through some sample problems, and then we'll test Monday, Tuesday. How about? Okay. Well, I mean, Monday's a short day, so you may finish it Monday. It's fine.